So it's going to be.
Should have tried those.
It's going to be in the second quarter. Add it to 9.
We might want to change it.
Yeah, we can. Oh, no, there's over there.
All right, circuits 1, people. Okay, so just a few tricks, and so we're not gonna go over your E shift or your current shift because I'm sure you got your solutions for your test, so you can review those on your own. You know, just go through your homework, go through the solution. What we will go over today is gonna be kind of name or name with phasors. So, you know, it's your name or name, but now you have inductors and capacitors. And you should go back and watch this video because I'm posting like my cheat sheet for when I took this test, you know, how to convert between inductors and how to convert to phasors. And also, Suzanne's gonna go over these, but how to go from time domain to phasor domain, especially if you have something like this, right? So what's the real part, what's the imaginary, you know, what's your omega t, stuff like that. And then this is also very helpful for your RL and RC circuits, which we're gonna go over, but these are just some tricks that are gonna help you because I don't know if you've done it in your homework. You have that little table you have to fill out, like what's your capacitor voltage at t equals 0 minus, 0 plus, and infinity. Right, you guys? Is that the homework you're on right now?
Yeah.
Okay.
It's over.
Okay, yeah, but that's what's gonna be on your final.
Yeah.
So this is what helped me how to solve those problems. And, you know, I even give you like what your tau is, because one thing that tricked me for the tau of the RL network is that you use the conductance instead of the R. So, and these are also like helpful things. Your T at 0 minus and an RL, your inductor is a short circuit. It's not an open, you know? So, you know, in case you haven't memorized that yet, what exactly is happening. So if you want to go over this video later and try to write those down. Okay, so Suzanne's going to start with your first problem. So I'm going to give you guys a couple of minutes to write it down if you like, or take a note. And just off the bat, do you know what this looks like? What kind of network you're going to end up analyzing? I mean, what do we see there that kind of gives it away?
Tough crowd today.
He's going to be a name or a name? Anyone?
I said name.
Is this going to be a name or a name?
We got both.
We got both? Because I see here, I see in doc, yeah. What? Name?
Yeah.
Okay, we have current sources. And he also gives us G values.
Nodal.
Exactly, right? I mean, he kind of gives it away there. There's no voltage sources. I think he's even labeling the nodes, and he gives you conductance. So it kind of should give it away that you're going to be working with a name, right? Nodal analysis.
All right, we ready to start, guys? So we determined that it was going to be name, right? So what is our nodes here? So I tried highlighting kind of what we were given and what we could use. So with the frequency of 1 radian per second, is that frequency as an F or omega or what?
Omega.
Okay, good job. So we're given omega equals 1 radian per second. And let's say if you were to give you frequency, could you find omega? How? 2 pi f. Omega equals 2 pi f. So you can always translate between those two. So we have two.
And then, just for the reference, can you put an omega here so they know why omega equals to 1?
Here. Surveys in here. I just tap.
Yeah. Can anybody see why omega equals to 1? Because there's nothing next to the t, right? Because usually your argument is cosine omega t. And because you're only seeing a t alone by itself, your omega is 1, okay? That's not always going to be the same.
Mm-hmm. So in this, what he wants us to find is I3 of t in a time domain format. This right here, there should be an omega here, but since it's 1, he just kind of takes it all out. All right. So we were given omega, and we're also given jg of t, which is the current source as a sinusoidal function. So can we analyze that in MAME or name, depending on whatever? Can we use a cosine function?
We know we have to transform the phasor.
Okay, do we know the phasor equivalent of jg of t?
Yeah,
What is it?
there's 5 phasor 0.
Yeah, so 5 with a phase angle of 0. So this is considered in polar form. But you can either put it like this, or you can also put it in rectangular form, where it would be.
Why is the angle 0? Because if you had a phase angle, it will be next to the omega t. So it will be 5 cosine omega t plus an angle. That angle would be the angle that you have there. And since you don't have one, it's 0.
So that's typically the format of a phasor. So here in this case, our amplitude is 5, our omega is 1, and our phase angle is 0. So that's kind of where we got all our values. So I typically just leave it in polar, but you can convert it to rectangular if you want.
5 plus 0j.
Yeah.
It's just 5.
So 5 plus 0j, or I, depending on.
J, we're E.
Sorry, if you're in a math class, they'll put it as 0I, but in E, I is reserved for current, so this is 0j. So we have that part. Now, so we said we need to do name, right? So we have our node voltages labeled here very nicely by Dr. Russell. So what do we need to find? So we're finding this current flowing through here. So we need to find everything. So the resistors are already in terms of admittance, but our other elements are still unknown. So can we replace these capacitors and inductors with their admittances?
Yes.
How do we find that? Okay, what's the formula for, let's say, XL? That's like the reactance of a inductor.
Minus J times 1 over L.
No. Anyone else?
So minus J over, say it one more time?
Minus J times 1 over omega L.
He's right.
For the
So it's
C
1
or
over.
for L.
Inductance.
Oh, no, no, no,
It's
no, no, no,
J
no, no,
omega
no.
L. J omega L.
Okay.
Here, just go to the top and show them the little thing I made because they obviously don't know this.
This?
Yeah.
Yep. So we're looking at this right here for. I'm looking at the impedances, so that's J omega L. Admittance would be 1 over J omega L. And then,
Oh yeah, you were doing admittance. Okay.
but that, you had the negative J kind of flipped.
It will be negative when you put in your
Okay.
calculator, but if you put the J in the bottom, you know, because 1 over J omega L ends up being negative J over omega L, but then your J has to come to the top.
So you're right. It's
Yeah.
just, it's a little trippy.
Just plug it in your Inspire. It's your
So let's do IL3. So we said that's 1 over J omega L. So would that just be 1 over J? Omega is 1 in this case, and then our L value is just 1 Henry. So that's just going to be 1 over J. Or in this case, just negative J. So now we can do the same thing with the cap. So for Z of a capacitor, that's just 1 over J omega C, right? So if we wanted to do the admittance, we would just flip it to the top. And then that would be our value. So J omega is 1. Let's say C is 3 farads. We have J 3. Last one, best one. YC4. Can you guys do the last one for me? So now it's just J times 0.5. So now we have basically all our elements. So these are all our admittance values for our name. And then, so we have a dependent source here that's dependent on V2 and V4. Can we translate those over to what we need? What is V2 can be put in terms of? So what is V2? How can we put this in terms of node voltages in this one? The things we're trying to find.
Suzanne highlighted it for you. What is V2? It's the voltage across C2, right?
Yeah.
And what is that voltage to it? What does it say at the top?
So I'll give you guys this one. So it's going to be VN1, right? Because that's going to be the voltage here. So that node voltage is going to be the same across that entire capacitor. All right.
Make sense? What was that so hard earlier?
So same thing for V4. What is that going to be, that voltage? Exactly. Okay. So again, we're solving for I3. So even though we're solving for the node voltages, we want I3 in the end. So how can we find I3, which is the voltage, the current going through that inductor? How can we put that in terms of things that we're solving for?
VN2 minus VN1 minus. Or multiply by the admittance.
So you said VN2 times what?
It should be VN1.
Let's put a polarity on our inductor and maybe that will help us.
Which side has a plus sign?
Plus sign in the left.
Okay, good. Right. So right, whoever said right.
And then multiply by what?
Right.
Exactly. So now we have that. So right now what we're going to do is find these node voltages that we want and then plug them into that equation to get the final I3 T. So we can start generating our name.
But before we continue, do you want to flip the table? Because I see you're struggling to see. Do you want them to flip the table so you can be closer?
figure out how I can get this stuff in. So can we start putting together our matrix to find our node voltages? Okay, so what's the admittances going into the first node voltage? Okay. Okay. Okay, what's in common between the two? So then we just translate that over here. Now what's going into VN2? And? Okay. Just multiply that by our two node voltages. Okay. Let's shrink this.
The thing?
I mean,
The
like,
pencil.
the pencil, but like to have more shifting.
Yeah, just select it. And then you can make it smaller.
I don't
Yes.
like technology.
You're already on select mode. There you go. And you can also make it smaller. There you
Okay. So now we need to put our sources, right? So what are our independent sources? Zero. Okay, and then what is our dependent sources? Okay. So before we go on, can we put this in terms of what we're finding and translate that over? So what is that going to be? Remember, we said that V2 is equal to Vn1, and then V4 equals Vn2.
And GM equal to
Yeah. So how can we translate that? Right? And then same thing for the bottom. And that can just translate over to 2, 2, -2, -2, right? And now we can subtract that over to the right-hand side. So before we subtract, should we put all the values? Let's put all the values for impedances or admittances first. So G1 is just 1, right? YC2 we found to be J3. YL3 we found to be negative J. Negative YL3 is just negative J, so negative times a negative J, J, and then we have again negative J plus YC4, which is J.5, and then G5, which is 4. So we can simplify that down. What is going to be the first term? This is J, J, second term. Minus, right?
Yeah.
Okay. Then we have VN1, VN2, equals, what did we say our phasor for was jg of t? Right. And then we have plus 2, 2, negative 2, negative 2, 1, v, and 2. Right? So now, whenever we subtract, what is going to be our next matrix? Yeah. Okay.
This one.
There's the next one.
2 plus J.
Okay. And last one.
6 minus.
So at this point, what I do is I just plug it into my Inspire and get the values. I get Vn1 equals to negative 0.2 minus 2.4j. Then Vn2 is equal to negative 0.4 plus 0.8j. So now back to what we were looking for. We want to find this, right? So we need to do Vn1 minus Vn2 and then multiply by admittance, right?
Yeah.
So we do Vn1 minus Vn2. That gives us 0.2 minus 3.2j. And then we have I3 of t equals that Vn1 minus Vn2 times y, L3. And then this, again, was j from earlier. See right here. Right? So my I3 of t came out to be 3.20624 with the phase angle of negative 176.424. So now, how would we convert this to a time domain?
Actually, you should take the t out of there.
Yeah, yeah. So how would we translate over to a function of time?
Sine of omega 2 minus or plus
You said,
And that's your final answer.
so I have a question.
Yep.
So this one, I put it in the calculator.
Mm-hmm. Can you explain them how to go from like rectangular, like if they have 0.2 minus 3.2j into this form,
Okay.
So they need either in their if you have an inspired and you get a rectangular, you can go to polar. Just make sure you're either on degrees or radians, whatever Russell is using. You should be able to do that on an 89. Where's your calculator? Let's do it together.
So you could always do it by hand. So you can always find this magnitude 3.26 by doing what is it, the square root of the real part squared plus the imaginary part squared.
Right.
And that'll give you your A magnitude.
So I put this one here and inspired.
Right. I mean, you're accurate. That's not accurate. That's just Vn1 minus Vn2. But did you ever find the rectangular of I3?
Mm-mm.
Here, I can find here's in the calculator, if you have these, you just put parentheses, 3.2 at an angle. There's an angle symbol there, so you can put the angle, and that will give it to you in rectangular. Okay, and then if you want to go from rectangular to polar, you do. This is the symbol. It's right here. But if you want to do from there to polar, I'm just gonna go to catalog and look up P.
My question was that,
Mhm.
I'm confused about this listing.
Okay, so if you see, so whenever you do the calculations, you get it into this rectangular form, right? So the value without the j multiplied by it, that's considered the real part. And then the one that's kind of next to the j is imaginary, right?
And I do the,
Yeah, so you do the real squared plus the imaginary squared, all of the
so
squared.
before minus.
Yeah, so YL3, that's what we found earlier, the negative j. So you multiply that by this thing that we found earlier, you get this.
Okay, so everybody knows how to use their calculator? Okay. Any questions?
Is it me the next one, or is it you?
It's yours, but if you want, I can go first and then you can go.
So this next one here is analyzing an RC network. I don't know if you guys can see all that. You guys read this first. And then here's the circuit.
All right, from the top of your head, what is a capacitor at t equals 0 minus? It's from your homework.
Open, so
What about at t equals 0?
battery.
Okay, and then finally at t 0 plus or infinity. Okay. So with these three different things, we can draw three different circuits, right? So at t less than 0, so this thing switches at t equal to 0. So before that, what would be our circuit looking? What would our circuit look like? What would be our path? So we have this for sure. So this isn't connected. So we go here. Now we're here. Where does our switch take us?
Where would a current flow through? which path does current flow, which path will current always flow through if it has different options? The path of least, which is which one? Which of these three has the least resistance? The shorted one, exactly.
So now that's our circuit. So it takes the path that has nothing in the way and it just goes straight to ground. So now we can draw this with our sources.
But it wouldn't take all three.
No.
Mm-mm. That's why if you put a short with your next to your resistor in parallel, your current you're gonna short your resistor because the current's gonna go through the short.
What if it's in the middle?
Then it will go through the resistor. Oh, if there was a resistor in the middle, then yeah, you'll have a current divider because current will go through all three branches.
So what did we say our capacitor was? So this is our C3T. So I'm just going to start out by finding all the voltages and the currents for each scenario and then put them all together in the end. So it's plus minus mu VA. Okay. All right. So how would we find our VC3 right now?
Nodal analysis. What the voltage.
So we can just do a KVL loop, right? Oh, that's another method. So what is our VA in this scenario here? What is that voltage? -3 volts. Okay, so now we can generate the KVL loop. What is that going to be?
Put your plus and minus. Okay, we put our walking man on the plus sign of BC3 and we start walking our KVL. What's the first thing we touch? Right, plus or minus? Right, so. And then we need to choose a polarity for this resistor, right?
On which side? Okay.
Weird, but okay.
Wait, actually. Hold on. Are we going to have a voltage across that resistor? Yeah, so this doesn't even matter.
Just to,
Yeah, so whenever this is open, there's no current flow. Right? Remember that. So we have mu VA, and then we skip the R2 because there's no voltage drop. And then we go to the next thing, which is our source, right? So what is that going to be? So -3, and that equals our VC3, right? So we have mu, which is 4, times VA, which is -3, minus a 3. So our VC of 3 is just -15 volts. So that's one of the elements we need to find, right? Okay, so now what is going to be our current in this case of IC? Exactly.
and when you're filling this table up, there's always something that's going to be a 0 or like there's two answers that are always easy to find right away.
Okay, so now let's analyze the t equal to 0 case. So now that the switch is closed, what is the path that we're going to take? So switch is now here. Right?
Yeah.
So which way does the current want to go? Yep. And then now here. Right? Does that make sense? So now we can redraw that. So we have our current source, our resistor going, another resistor, our dependent. And then what does our cap look like right now? Yep. Okay. This is 2K. This is 6 minutes. All right. So what is our voltage at this time? And why is that? You're right. But why? Yeah, so capacitors resist change in voltage, so they don't have instantaneous changes. So remember how our capacitors are what, C dV dt? So we can never have this be, because if there's an instant change, that's going to make this go to some infinite value, and it's going to mess up your entire circuit. Okay, so now we have this. What is going to be, how are we going to find our current? Okay. It's going to be 2K. What is going to be our voltage? Mm-hmm. Okay, so just to make our lives a little easier, what is VA right now? Mm-hmm. So it'd be 12 minus 2K times our current, right? So now we have to find our IC of 3, right? So I think the easiest method now is just to do a KVL loop again, because all of these have the same current, have all the same current, right? So can you guys help me develop a loop? So
It's 2K
okay,
plus 1K times R.
And then minus.
Okay.
7
and then what about our source over here?
and then plus negative.
That equals 0, right? And then our VA is going to be negative 12 plus 2K IC3 minus mu times 12 minus 2k IC3 minus 15 equals 0. So can we move these all of the IC3s or everything that doesn't contain IC3 to one side? We can do IC3 times 2k plus 1k. And then what is going to be from this equivalent? So mu is 4. Yep, plus 8k. And then that's all of our IC3 values, right? So now that's going to equal to 12 plus 15. And then our last one from this thing. So the 2k is just for this part. So it's just going to be 4 times 12. So negative 48, which we shift to the other side, so we'll get plus 48, right? So what should be our IC3 at this time?
Over
11K, right?
So so that's like 6.818 milliamps, right?
Mm-hmm.
So this is that t equal to 0, t equal to 0, right? So that's the second set. So we've already filled out this, and now we're on to this one. So at
Unveil your answers.
oh, some of them are
Anyway.
wrong.
Oh, they were?
Yeah,
I thought you got like.
this one's right. This one's
Okay.
right. This one was wrong.
Wait, no, not unveil that
Oh,
one.
sorry.
Okay.
Boom, boom. Okay, so now at t equal to infinity, so we're still in the same switched position, but now our capacitor looks a little different. What is our cap going to look like? So we can redraw it like this if we want, or we can just go straight to our transformed one from here. And we said it's an open. This one is okay, so now what is going to be our VC of 3? So what is our VA at this time? Exactly. So now we can find VC3. What is that going to be equal to? What's the equation?
Come on, guys, you got these. What is BC3? Put your walking man.
Pick a direction.
Where's the plus sign? Yeah, start from the plus sign of BC3 and go to the negative.
Positive.
Mm-hmm.
Yep, because remember we have no current flowing because it's open, right? So that's that. And then we know our VA is 12 and we know our mu is 4. So we have 4 times 12 plus another 12. What is that going to give us?
60? Quick math. I did it in my head, guys.
So VC3 equals 60 volts at this time. So now what is going to be our IC3 at infinity? Exactly. There you go. That's most of the problem done. So now it also wants us to find our tau value, right? So how do we find our tau?
Tau?
So what is the equation for tau in general? Right. So what we're going to do is we're going to analyze the circuit. So whenever we want to find our equivalent, we're going to short out all dependent or independent sources and just analyze the circuit. So looking at the t equals infinity, we have plus or minus VA. Another one. And then we can represent the cap as a current source for now. Because really we're just looking at the resistance coming in here, right? So this is kind of like a Thevenin's equivalent. Yeah. So to find R equivalent, we're going to have to find V out, which is just this, divided by J out, which is just some dummy variable, dummy source that we made. So here, right? So now, how would we find V out in this case?
It's basically the same way you've been doing all along, almost.
So we can start by just doing our VA, right? So the voltage across here. So this is, remember, a series circuit. So all the current is going to be equal to this current, right? So what is our VA? Okay, so that's R1 times J out, right? So now V out, if we do our KVL loop, what is that going to give us? We put our little man here. He's walking. What does he hit first?
Don't say it, let them answer. Come on, guys, somebody else. You're plus what? All right, thank you. You're almost there.
Okay, and then what's next? Does that make sense? 100%? You saying that just to make me feel better? So we're just doing a basic KVL loop. So we can add the resistors, or you can do R1 J naught plus R2 J naught. It's the same thing. All right. So now we can plug in our VA, which is just R1 J naught. Right. So now what can we do here to get our equivalent? There's an easier method here just to get J naught out of the picture completely. Remember this formula here? So can yep, exactly. So we can factor out J1 plus R1 plus R2. All right. So then if we divide by J naught, what is that going to give us? Yep. So do we know all these values? Yes or no, team? So R1 was equal to 2K, R2 is equal to 1K, then mu is equal to 4. Can someone give me R equivalent? Okay. I'm only hearing one person. This isn't fair.
He's gonna get all the stickers.
So now we have this. Do we have enough information to find tau? Why not? But we were given that, right? Which is 220 microfarads, right? So now we can just plug it in. And then what is our final tau value?
Whatever that multiplication is, right?
It's a 2.42 seconds. So that's tau. So that fills out our table, right? I don't think I got it right, but we'll see it. Yep. So now the second part is we need to find the time domain expression for VC of 3, VC3 of t. So with Monse's cheat sheet that she gave us earlier, hold up. This is the equation that you need to know. Do we have all of these values? Yes. So can we just plug and chug? So VC3 is equal to VC at 0 minus VC at infinity e to the negative t over tau plus VC at infinity. So VC at 0, we found that to be, yeah. And what is our VC at infinity? $60, yep. And then e to the negative t over tau, which we found to be 2.42, plus VC at infinity. Yep. So VC3 of t, we can simplify that down to plus 60 minus 75. Negative 2.
Yeah, no, it's the same. Right? No, 60 minus 75. This is that part that on front.
Okay, yeah. Yep. Does that make sense, everybody?
Yeah.
So we're going to ace this problem.
I will say this is a little harder. The trickiest part about the one Suzanne just did was the dependent source, because if there wasn't a dependent source, then your R equivalent would have been much easier. You wouldn't even have to do these. If you hadn't given a dependent source, which I think on the next one you'll see, your R equivalent is simply R1 plus R2, right? Because there's two R's in series. So this one was tricky because of that. I consider this a harder Russell problem for sure. But other than that, these problems are simply circuit analysis, and it's mostly KVL, KCL. Okay, it's nothing you haven't seen before. We're now gonna do an RL. So this was an RC, now we're doing an RL. So I'm gonna give you a couple of minutes to look at the problem. So we have an RL network that has been at rest for a long time. At t equals 0, we're gonna flip a switch, calculate values for I4 and B4T, write the complete time domain expression for I4, sketch as accurately as possible the time domain waveform, calculate the value at T1 such that the value of the inductor current is 0, calculate the value of rise time. So we have a lot of stuff to do in this problem. But these, let's go ahead and get started. So this is your network. Okay, so at t equals 0 minus what do we have? Right, everybody see that the rest of this is open, right? It's connected to that, right? Okay. So our circuit can be simplified. Oh wait, what's our inductor at t equals 0 minus? That's right. And what happens if you have a resistor in parallel with a short circuit? We just talked about this earlier. No, what's close? What path would current take? Exactly. So the resistor goes away, right? Oh, sorry, the resistor goes away. Okay. Okay, so we're trying to find, remember we're trying to find B4 at t equals 0 minus and I4 at t equals 0 minus. So what is B4? What is the voltage through a short? Yeah, thanks. Everybody knows that the voltage through a short is 0? Okay, perfect. So remember I told you in this table there's gonna be two values easy to fill out, and that's the voltage through a short and the current through an open, okay? So on both of your tables, now we have a 0 here. Oh, we have a 0 here, and remember, oh, not here, sorry. And remember on Suzanne's problem, she had a 0 here. So right off the bat, you can get like 5 points just by knowing where to place the 0, okay? That's some freebies. Okay. So what will be the current through this branch? Yeah, smart. But we also need to make sure our polarity is right, right? Okay, so it will not be 9, right? It will be, right. So I4 of t is right? Okay, and that's okay. Everybody happy about this? Okay, so we found two values for our table. That was pretty, and this problem is easier than Suzanne's problem, so that's why, but that's why there's a lot more parts to it. So now that we've done this, we can do our network at t equal to 0. And at t equal to 0, we move the switch, right? So now our switch is here. And this goes away. So our network is going to be, oh, sorry. Make sense? Make sense why that's our network? Okay. Okay, so, and what's the value of this current? Right. And the current's going down because that's the direction I chose, okay? Make sense? Okay. So then we have our resistors. This is 3K, 2K, and this is 1K. So now to find our, remember what we're trying to find. So we were trying to find the voltage across here, right? And we're also trying to find the current through that, which we obviously know what the current is. But to find the voltage across that, I think the easiest thing to do, anybody has any ideas? We have two current sources. What can we do with current sources? We could, or we can also turn them into voltage sources. Right. I mean, yeah, there's also a resistor here, so we wouldn't be able to, right? Everything has to be in parallel. So this guy would have to be in parallel here. But we can, because you have these two guys in parallel and two guys in parallel, you can make them voltage sources, right? Okay, so, and that's gonna make our life easier. This guy here. Okay, so let me put some values. So this guy was 3K, 2K, 1K. And this guy was 10 before, so now our voltage is 10 times 3, which is 30, right? And then this guy is negative 4.5 volts. Okay, and remember the voltage we're trying to find is the voltage through the inductor, which is the same as the voltage across the R, right? Because they're in parallel. So it's still that voltage here, right? Does that make sense to everyone? Okay. Because that would have tricked me on the test. I would have probably ignored that and say, oh, it's 4.5, but it's not. Okay. It's the voltage across all these branch now, since it's the same as the voltage across here. Okay, so doing KVL, we can solve these pretty easy. You can solve for your current if you want, because at some point you're just going to end up, the voltage that we want is from here to here, right? So it's just going to be R, well, 1K times IM minus 4.5 volts, right? Minus, sorry. That makes sense? Why is minus? Okay, so let's go ahead and figure out what our current is. So I'm going to put our guy here. And we're going to start this direction for KVL loop. So what's my KVL? Positive or negative? I'm going to touch the negative first, right? Make sense? So negative 30 volts and then plus 3K I1, IM or whatever, plus 1K IM minus, I'm just going to call it a plus, okay? But you know what I did. 4.5 volts. And then plus 2K. Right? So this is okay. Any questions on how we did that? Everybody knows how to do KVL? Okay. So now, again, we're trying to find B4T, right? So what did we say that voltage was? Right. So this is just 4.25 volts plus 4.5 volts, which equals 9.75? 8? Sorry. Quick math, sorry. Okay. And then what we also need to find, well, we found already the current, right? So now we can put our values. So this guy stays the same. And this guy is 8.75. And so the other thing about these tables, besides having one value that is 0, these two values, whatever you found at 0 volts, at 0 minus and 0 plus is going to be the same for both the capacitor and the inductor, okay? But kind of flipped, if you know what I mean. So in this case, the current stays the same. In the capacitor, the voltage stays the same. Okay, and your other cell is 0. So if you do the first part right, you get like 15 points just out of there because you know these, and then you also know these. Okay. All right, so let's do our next network at t equals infinity. So at t equals infinity, our inductor becomes a what? A short, right? So it's the same network as a t equals 0, but we replace our inductor with a short, okay? So now our network looks something like this. So what's the voltage through a short? What? Yeah. So right off the bat, we can answer that question again. That's a freebie, but we do have to find the currents through our short, right? So what when you have a resistor in parallel with a short, what happens? Right. So I'm just gonna go ahead and delete that guy. So this is our network, right? So the current through here is the same current as this resistor, and I'm just gonna go ahead and kind of draw the circuit better. So let me, and my values are 3K. So a way that will help me see this circuit better, or this network, will be like this. And how do we find what the current going through here is? Right, current divider, right? So the current is simply, and the value of this guy is 10 milli. So we're gonna call it I4. I4 is equal to 10 milli times, which impedance do I put on the top? Yep, and on the bottom? Right, perfect. So that's pretty easy, right? That is just 6 milliamps. So we are finally done with our table. So we said voltage was a short, so 0, and this guy is 6 milli. So now now we need to find our time constant. So, and for that we need to find our equivalent, and this is where I told you this problem is easier than Suzanne's problem because we don't have any dependent sources. So it's relatively easier. However, you need to remember that the formula for tau for an RL network, which is in the formula sheet I gave you for free for assisting here, is here. Oh. And I even put you warning signs to remember it's G and not R. Okay, so at t equal infinity, we have our network at t equals infinity.
Would it be negative 6.6 million
What would it?
for the current and then
Um,
our original current direction downward?
oh, sorry. It should be the current direction that I'm choosing is this. I think I've always chose it like that. Yeah. Yeah. And it was, yeah, given here. So it is 6. But yeah, on this one I had it flipped, sorry. Okay. So so our network got infinity. Let's look back to that. And then you also have to shorten your or open your current sources, shorten your voltage sources. In this case, we only have a current source, so we're gonna open that. And then we have this resistor here. So this is our equivalent that we're trying to find. So can somebody tell me what is our equivalent? You guys should be experts on these. I'm gonna let you answer these, okay? Because this is your test 1, 2, and 3. I'm gonna actually go ahead and give me the actual value of our equivalent, and whoever gives it to me first, I'll give them a cookie. Robert's calculating. Robert, you can participate. It's a chocolate chip cookie. Robert's like,
1.5?
No, it's not 1.5. I have no rush whatsoever. Yeah. Okay, what is that? You have half the cookie.
Calculator 4.
Okay, but you said it right. It's the 5 in parallel with the 1. Did everybody see that? Okay, you get the cookie. Okay, but now, since he doesn't have a calculator, you guys tell me what the value is going to be. But now you know.
0.8.
No. But close, but those are not the units. 0.833 kiloohms, so 833. Okay. Thank you. So do not put it in your calculator as 5 times 1 over 5 plus 1, because if not, you're gonna get the wrong.
I do that in I do it in the most logical units. I don't have to enter a bunch of zeros.
Well, it will give you the wrong answer unless you can do it in your head.
Afterward, I add a bunch of zeros.
Okay. If you can do that, then go for it. Okay, so now that we finally find our equivalent, now let's find G equivalent. So what is G equivalent? Yep, smart. Okay. This turns out to be 1.2 millisiemens. Okay, so now our tau is, now we can finally do our tau, which is G equivalent times L. And you saw how much easier this was than Suzanne's problem, right? We have to do the fancy G-knob and sulfur stuff because we did not have a dependent source. If we had one, we will have to do a lot more work. So this turns out to be 1.2 millisiemens times 680 microhenries. And this is... Okay. So again, so this is you completed your table. So now part B is write your fully time domain thing and sketch the time domain waveform. I'm not gonna sketch the time domain waveform, but so our time domain, as Suzanne mentioned before, should be here. Oh, I guess not technology. Okay. Okay, any questions? This is just your formula and you plug in your values, your I at infinity, your I at 0, and so on. Okay, and if you wanted to plot the thing, so we can see that we start at negative 4.5 and at some point we're gonna converge to 6 milliamps, right? And ideally, this is your time constant or something like that, of that matter. I don't know. Don't quote me on that one. Okay, so part C, because this problem was easier than Suzanne's problem, this has more parts, okay? So, and you have more time for your final. That means he has more time to give you questions. So part C is calculate the value of T1 such that the value of the inductor current is 0 amps. That is the value of T1 for which ILT1 equals 0. So we go to our fancy formula we just derived. And so what we're trying to do is, so we have this, right? So we're trying to find this for when this is equal to 0, right? Right? So we're trying to find at what time our inductor current is 0. Right? Ever make sense? So we just solve this equation for t. Yeah, natural log of natural log. That's right. So I'm not going to go through that because I know you guys can do math, but I'm going to give you the answer. You're welcome to do it later. So make sure you solve for t correctly. And part D, Russell loves this one. What is rise time? Does anybody remember the formula for rise time? Yeah, wow, you learned something in this class. I'm so happy. At least you learned this. Okay. And this is nothing but, oh, also, sorry, this is wrong units. Nanoseconds. Yeah, so your TR should be, your rise time should be 1.79 microseconds. Okay, I'm glad if you didn't learn anything today, at least you know this.
Make sure. In the RLC, like, which one is, like, make sure you get it right?
Make sure you get it right. What do you mean?
So that at 0 minus equal to 0 plus, right? If we got this one, if we got this one,
right? Yeah. So I'll show you again the table. So this is for an inductor, okay? For inductor. For your inductor, your B force T is always going to be 0. And this value that you found here, and this value that you found here is going to be the same here. And then for your inductor, D should also be 0. Okay, so those are 4 things that could go right for you in this problem if you solve for these right. If you don't, then you're screwed, but hopefully you can solve for that one right. It's just probably, KCl, KVL. And for your capacitor problem, your current is 0, not your voltage. Your current is 0 because you're in open, right? So it's going to be 0, 0 here, and whatever value you find for your voltage is 0 minus is going to be for 0, okay? Was that your question? Yeah. Okay, and then, and I think I don't know if I summarized these. I said, usually ICT equals 0 at 0 minus and at infinity. So in my little formula sheet that you can go in the video later and copy down, I have those things written down for you. BLT for an inductor, BLT of 0 equals 0 at 0 minus and infinity. For the capacitor, ICT equals 0 at 0 minus and infinity. Okay, so that's 2 answers on your table. You get right if you copy these. Okay? All right, any questions? All right, good luck.